Hello, fellow calculus students. My name is Drew, and today we're going to discuss the disk and washer method of rotational volume. So, without further ado, let's get started. So, we have a sample problem that's telling us to determine the volume of the solid obtained by rotating the region bounded by this function, x equals 1, x equals 4, and the x-axis all about the x-axis. So first, let's take a look at what the graph looks like. Right here, we see we have a part of a parabola, the cross-section from 1 to 4. And we're rotating this about the x-axis. So let's try to imagine what that would look like, which is something I'd recommend that you do for every problem, because it always helps to have a visual picture of what it looks like and what you're dealing with. So to do that, you would first want to reflect the graph over the x-axis, or whatever axis you're rotating about. And then you want to draw surfaces like this, and you get a pretty decent visual picture of what it should look like. And I actually have a properly generated 3D image, and while our image isn't perfect, we get the idea of what it's supposed to look like. So the hardest part about taking the volume of this is it's not a simple 3D figure like a cube, a cone, a sphere, etc., nor is it made up of these simple figures. It is a complex figure in and of itself. But the good news is that we can find the full volume of this quite accurately, and it's quite a simple process too. It's not as messy as you guys think, trust me. But before we do this, let's look at the same problem or similar problem from 2 dimensions. So by now we're very familiar with the problem of finding the area under the curve. We started off by approximating it using small rectangles, with which the height will be the function at the point, whether it's the right or the left endpoint, because at a really small value, it doesn't make a difference. Multiplied by a really small value, dx, which is essentially an infinitesimally small value. So what happens as these rectangles get smaller and smaller? They almost look like a line, actually, as they get really thin. These rectangles perfectly fit the curve, and by summing up an infinite number of these rectangles, of which the area would be the function at that point, times dx, from your left bound to your right bound, from A to B, you find the total area under the curve. So, let's try to do the same thing with 3 dimensions, right here. First, we can try to approximate this using small cylinders, with which the area of the base would be a function called a of x, and the height would be dx. By integrating a of x dx from your bounds, you'll find the total volume of this region. And it should make sense, because as these cylinders get smaller and smaller, they approximate, or they get closer and closer to being a circle, or in this case, a disk, hence the name disk method, just like this. And as you sum up an infinite number of these infinitesimally small disks, it makes sense that you end up totally finding the volume of the figure. So, to find this volume, what we should do is we should take the integral from 1 to 4 of the area in terms of x with respect to x. Now, let's try to find a way to represent the area of x in terms of x. So, what we know about these disks is that it's a circle, and the area of a circle is pi times r squared. And the radius of these disks is simply the height of the function, or in this case, y. So we can substitute y in for r, so it will become pi y squared. And I'm going to move this right over here. And we can substitute it further, as we know that y is x squared minus 4x plus 5. So we know that the area in terms of x is equal to pi times y, which is x squared minus 4x plus 5 whole squared. So, the final piece of the puzzle, or final piece of this problem, is to integrate from 1 to 4 this function. I'm taking the pi out because it's a constant with respect to x. Now you could do this, the fish squared. Now you could do this by hand, but for time's sake, I'm going to do this on my calculator, and when you plug it in, you're going to get approximately 49.009 units cubed. So to recap, what we did is that we separated this volume into small disks, each with the radius of the function's height and the area of pi times the function squared. And what we did is we integrated this function over the interval of the bounds, and that allows us to find the volume. And this right here, I'm just going to move this over here, is the general formula of disk method. And as you can see, it's very clearly derived from the area of a circle, and it's actually quite simple when you think about it. However, most students get confused by these units as they often try to memorize these formulas blindly, and they get confused between each formula and the application of each formula, and all of a sudden, they're trying to memorize which formula to use when, and while that route could work, it's a road that's going to lead to a lot of stress and complication. And I would recommend for each problem, just look at the problem, try to find a function to represent the area, a way of slicing up that 3D figure into a bunch of even areas, and integrate that area over the interval. And that's what's going to lead to a lot of success in these kind of problems. Moving on to our next example, we can see that this example is very similar to the last problem, except for two differences. One, we have two functions instead of one, and we're trying to take the volume or take the area of that and rotate that about the axis. And the second difference is that this time we're rotating about the y-axis instead of the x-axis. So that means all of our calculations will be in terms of y. And for that, one thing that we can do is that we can convert these functions so that they're in terms of y to make it easier to when we're doing our calculations. So this would be the same as x equals y cubed. And from this, we know that x equals 4y. And let's take a look at how these two graphs interact. And let's take a look at a 3D figure when it's rotated. So as you can see, it's like a bowl-like shape right here. Kind of like a cone-ish, bowl-ish shape. Like a bowl with the cone taken out of it. And right now, what we're trying to find is the volume of the outer figure right here. This section right here. And what we can do for that is we can split it up and rather than discs into washers. So it means there will be an outer disc and an inner disc. And I have an image of the cross section of what that would look like. So that would look somewhat like this, where there's an outer disc right here, which the outer radius will be represented by the x value of this blue function, which we'll call x of b. And the radius, or the inner radius, will be represented by the x value of the red function, which we'll call x of b. Or x of r, my bad, because it's the red function. So, if we draw this out as a washer, we can see that this is x of r, or sorry, x of b, because x of b is outside, and this is x of r, or the inside. So what we know is that the area of this disk right here has to equal x of b squared, or the outer radius squared, minus x of r squared, all times pi. Whoops. And if we integrate this with respect to y from 0 to 4, because the function, or from 0 to 2, because the y-axis goes from 0 to 2, we'll get the volume, just like last example. So in order to do this, we're going to need to find x of b and x of r in terms of y. So we know that, and we did this in the last part, we know that x of b, or the outer function, is the same as this linear line, which would be x equals 4y. So we know that x of b equals 4y. And x of r, which is the inner function, or the cubic function in terms of y, would equal y cubed. Now we have all the pieces and we can put it all together. So we know the volume has to equal the integral from 0 to 2. And remember, it's 0 to 2 because we're going on the y-axis. And from the y-axis, the figure takes up the space from 0 to 2. So we're going from 0 to 2, and we're taking pi out as a constant of 4y squared minus y cubed squared. And when we calculate this, which you could do by hand, but again, for time's sake, I'm going to do this through my calculator, we're going to get the answer of 76.595 units cubed. So as we can see, this is very similar to the last problem, except instead of one disk, we have a washer, which is basically an outer disk minus the inner disk. And what we did is we found a function to represent the radius of the outer disk and a function to represent the radius of the inner disk. We know that area would equal pi times the outer disk squared, the radius of the outer disk squared minus the radius of the inner disk squared. And when we integrate this area, we're essentially integrating pi times the integral from a to b of the outer radius squared minus the inner radius squared, dy, or dx, if it's in terms of x, but in this case it's in terms of y. So this right here is the formula for washer method. And as you can see, it's very, very similar to the formula that we derived for disk method, which would be just pi times the integral of r squared. But the difference is that there's big R squared minus little r squared because we have to factor in the inner disk, which we don't want the volume of. So now moving on to our next example here, which is to determine the volume of the solid obtained by rotating a region bounded by y equals 2 times the square root of x minus 1 and y equals x minus 1 about the line x equals negative 1. So as we can see, another complication that's added here is that we're not rotating about the x or y axis, but rather another vertical line, which in this case is the line x equals negative 1. So this makes it more complicated, as if we look at how the cross sections would look, we're increasing both the outer and the inner radius by 1, which means that the volume of this shape would take up more space than if it were just rotated about the y-axis. And this is a complication that we have to take into consideration. So as we know before, the volume would equal the integral from a to b and pi out front of the big radius squared minus the little radius squared with respect to y in this case, because we're rotating it about a vertical axis. So we know that our a and b values are 0 and 4 respectively, because in the on the y-axis, this figure takes up the space from 0 to 4. So we know that this would equal the pi times the integral of 0 to 4. But we still need to find what the big radius and the little radiuses are. So if we look at this disk from the top perspective, we can see that the big radius right here would equal the x value at this red function, which can be represented by x of r, and let me actually change this to the red color, x of r plus 1, because as we can see, we have to add this extra 1 because of the axis being shifted over left by 1. Similarly, for the inner radius, it would be x of blue, the x value of the blue function plus 1. So now we can plug in this formula, because we know that this would equal the outer radius, this will equal the inner radius. And we can also find out what x of r and x of b are. So x of r, let me do this in red, x of r would have to equal, we're given the function in terms of x, but we can convert it to terms of y. So we know that x of r would be this function, because x of r is the linear function, and this is clearly the linear function. So we know that x would equal y plus 1, or x of r would equal y plus 1. Now to find x of b, we would convert this to terms of x, just like we did for this one right here. So this would be x of b minus 1. So you divide each side by 2, so you get y over 2 would equal the square root of x of b minus 1. Square both sides, you get y squared over 4 would equal x of b minus 1. So you get ultimately that x of b would equal y squared over 4 plus 1. So you know that x of b equals y squared over 4 plus 1. And once again, x of r would just be y plus 1. Oh, if you notice, they gave us these formulas right here too. The outer function would be x equals y plus 1, and the inner function would be x equals 1/4 y squared plus 1. So now, we know that the outer radius, which we can write over here, would equal x of r plus 1, and we know that x of r is y plus 1, so it would equal y plus 1 plus 1. The inner radius would equal y squared over 4 plus 1 plus 1, because y squared over 4 is x of b, and the little r is x of b plus 1. So this would ultimately, this would equal big R would equal y plus 2, little r would equal y squared over 4 plus 2. So now we're ready to substitute these values in. So this would be pi times the integral of 0 to 4 times r squared. R squared. So we know big R squared. So big R squared would be y plus 2 squared minus y squared over 4 plus 2 squared. And we're doing this with respect to y. And you could, once again, do this by hand, but I find that it's much easier to do by calculator. And when you calculate this in your calculator, you get the result of 60.319. 60.319 units cubed. Just to recap, what we did here is that since this axis of rotation was shifted one to the left, we see that the radius bigger and the inner radius was increased by 1. So first we find a function to resemble the outer radius and the inner radius in terms of y, because we're reintegrating with respect to y. And when we find that function, we add 1 to it because this radius is being increased by 1. And what we do is we plug that into the formula which we derived earlier, which is essentially just finding the area of this disk. And we integrate that with respect to y. So we're summing up all the little disks like this until we find the volume of the total section.